And when we talk about energy transfer, we that's basically what's happening with waves, right? It's transferring energy through matter itself. And so, a lot of times it can transport energy quite efficiently. And we can see that as an example where we have the ocean waves. You have a hurricane out way, way, way out in the Atlantic, and the energy is coming out from those waves through the water, and then it hits our coast. And so it can still be pretty far away, but we could be getting some pretty strong swells coming in, and that's because that energy is being transported pretty effectively through the water. The rate at which the energy is transferred depends on the amplitude, right? So the greater the amplitude, the greater the rate, and so the more energy it's going to have. And those ocean waves that are coming from a hurricane are typically much larger amplitude, more energy, and it could be even dangerous to be in the water at a certain point. As the waves spread out, they do diminish over time. So, the amplitudes get less and less over time. Now, refraction of waves is where we have transmission from one medium to the other. So in the top clip here, or the top picture, you can see a wave that's going from a thicker medium to a thinner medium to a thicker medium. And if you notice, the wave actually slows down here as it goes, as compared to here, where you have a wave hitting and then it's taking off quite quickly because the medium itself is less dense. So the idea of superposition is where we have two or more waves that pass a particular point in a medium simultaneously. And so what will happen is that medium, right, can't be in two places at one time. So it's going to be a combination of those two amplitudes to give you a final amplitude. And the waves themselves actually interfere with each other and then can pass by and keep on going like nothing happened. So the different types of interference, we call one of them constructive interference. That's when they're in phase. That, in other words, that the amplitude is increased. That means that the amplitude is on the same side for those two waves that meet. Destructive interference is where they're out of phase. That's where you have a crest and a trough, and they interfere with each other and actually decrease the amount of energy. We know that a piece of matter can't occupy two places at one time, and so that's why we have to have the combination of these two waves, and yeah, then we get that combination there. So the superposition is again the overlapping of those two, and we'll see that here. So if we have a wave that here's the sequence starting with A, this wave meets this wave. As they start to overlap, you can see how the medium is starting to overlap with the addition of those two amplitudes. In part C here, they're completely overlapped. You have a very large crest. And then afterwards, they continue like nothing ever happened. And that's really important because this wave right here, continues on after it interfered and continues on. This one continues on like nothing ever happened either. So let's say that the amplitude here was like 1 meter, and let's say this was half a meter. Then our total amplitude would be the combination of those two would be 1.5 meters for the total amplitude. Here's another example of constructive interference. We have these two waves, this one and this one. They combine together in the middle. We have a great, a huge crest in the middle. Then they continue like nothing ever happened, and they can keep going like nothing ever happened afterwards. Now, destructive interference is where the displacements are on opposite sides of the equilibrium. And so this is where, they're destructing each other. Here's, part A here. We have a certain amplitude. Coming here, we have a trough, and when they meet in the middle, it's smaller, right? So if this was, let's say, 1 meter, and let's say this was half a meter, then this is below, so the resultant would only be 0.5 meters, and then they continue on, like nothing ever happened, just like we had before. Now, what's interesting is if you have two waves that are equal amplitudes, right, but opposite phase, if you crest and a trough, you could actually have it to where it's completely calm in the middle for a moment. Now, after they pass by each other, they continue like nothing ever happened, right? They're just continuing here. But in the middle, if you have the same amplitudes, opposite phase, they're just going to continue like, or they're going to actually make a completely flat surface in the medium. Wave plus wave equals no wave, or well, wave plus wave equals just basically a smooth surface. And so that's a little counterintuitive. It's a little bit interesting to think through that. Now, if we want to add up to a couple waves that are in phase, we could draw these out, and you could draw that out. You have the two waves there, and what we do is we draw a third graph like this, and when we add up these amplitudes, this is how we do it. We say, okay, this first spot plus this spot, let's say these two waves are right on top of each other. If they're right on top of each other, equilibrium plus equilibrium equals equilibrium. But then the next part, plus amplitude, well, those two are going to add up to be 2 times A, right? So this would be twice the amplitude. You'd have a spot right here. Then if you have equilibrium plus equilibrium, you'd have equilibrium. Trough plus trough would be a double trough. Equilibrium plus equilibrium would be equilibrium. And you do that with every spot, right? So you'd end up getting a wave like this, and a combination of those two. Now, destructive interference, if we have two waves at the same place at the same time right on top of each other, we do the same thing here. We draw a third graph. Equilibrium plus equilibrium is equilibrium. Crest plus trough is equilibrium, right? Because you have positive amplitude plus a negative amplitude equilibrium. Equilibrium plus equilibrium is equilibrium. Trough plus crest equals equilibrium. So what would happen is, in this case, it can be completely flat, right? Because these are destructing each other perfectly. The top wave and the bottom wave completely destructing each other. All right, so let's go ahead and try this one. Let's say we have a wave like this. We have equilibrium, and we have a wave like this. And we want to get the combination of the two. So what you're going to do is set up your third graph, just like you did before, and add up each of the points. Maybe only go to about right here. This would be enough. And add the two, the top one and the bottom one. We'll see how you do. So go ahead and pause the clip, give this a try, and when you're ready to check, you can hit play to continue. All right, so you should get something like that, where you have the equilibrium plus equilibrium. Well, equilibrium plus equilibrium is equilibrium. Positive 0.5 plus positive 1 is positive 1.5. Equilibrium plus those two equal equilibrium. Trough plus trough is a 1.5 meter trough, adding up to 2 amplitudes, and so on. Okay, so now we're going to add these two waves together, the dashed line one and then the solid line one. And to do that, when we draw the third, or draw what the superposition of those two would look like, we can draw that below it. So we add equilibrium plus equilibrium, equilibrium, this spot plus this spot, this spot plus this spot, and so on. And so why don't you go ahead and try that up to this point right here, just this section, and add up each of the different points. I'll do one over here like this is equilibrium plus equilibrium. That's going to be equilibrium there. So you can do the spots in between, and let's see how you do. So go ahead and pause the clip, give that a try, and then you can hit play to see how you did. All right, so when you add them up, you should see something like this, where you add up